but this is one of the fundamental topic as well that we want to discuss here. So idea, what is the idea of this topic and how do we discuss, how we will handle it, I will cover now. Okay, so student, this is how we have to deal with. Number one, the topic is called numerical. Although in a course contents, the title was mentioned as a numerical integration and differentiation, but basically we have to deal with numerical integration. Okay, yes, it is the same integration that you are used to of it, but do not need to be worried. We are not going to use any analytical approach. We are not going to integrate by using UNP or any other. We have some smart strategies that can give us approximate answer rather than we have to solve some complicated problem. Okay, students. So let's have it, because this is something new topic, has nothing to do with operators and difference equations. I mean, we are moving in some other dimensions now. So let me create some background about this topic, like what we are expecting from it. Let me tell you that this is the new topic, and that topic needs to have in this topic we have to cover two aspects. One is the numerical integration. How do we numerically solve the integral problems? And obviously we also apply, once we know the numerical integration, you all know that we can apply the technique to solve the differential equations as well, because in differential equation you need to numerically integrate, you have to integrate them, but here we will do some numerical techniques. Okay, so in this topic, that is numerical integration, we have to discuss two aspects. Number one, is that part we have to discuss is called integrations. Okay, obviously they are all numerical integration. You can divide it like that. And the other part that we have to discuss is solution of ordinary differential equation. It is not difference equation, is a differential equation. Okay, okay, so this is the differential equation. So in this topic, it is a very vast topic, but for our course point of view, we just need to learn few methods, how they apply and what are their instructions. Similarly, in this heading, we also have to discuss two or three methods that we have to apply for the solution of ordinary differential equation. And most of the ordinary differential equation in our case is first order. Okay. Now, also the method we are going to discuss may be used to extend to higher order, second order differential equation, but our prime focus for this course is towards the first order. So these are the two topics in lecture number 6 that we'll try to cover. I mean, it will start from today. Maybe I need lecture number 7 as well to cover these two things. Okay, so that's the main uh, uh, point. That is, you should know, if I'm talking on numerical integration, means that what are the topics included in this topic. So one is simple integration. I think I should write it down like that: integration of function f of x. Okay, integrate करना. We have to integrate those functions like f of x and a numerical solution of differential equation, usually first order. Okay, but whatever concept we will discuss, we will extend. But the common point in those, in the all of these strategies, that we will try to get approximate answer. Okay, we will try to get approximate answer. Also, our logic is like that. If we can do some extra effort, then we can make it very close to exact. But always, whatever the accuracy we want to impose, we get approximate answer. Okay, but they are very good resembles to the exact answer. Approximate answer. Now, when we are saying approximate answer, it is quite clear to you. I have used this strategy many times. This means that I want to compute numerical approximation. Okay, numerical methods or numerical techniques, keep in mind this thing. Okay, the one thing that I forgot to point out, the course outline that I shared with you, it has a heading of this topic is numerical integration and differentiation. I am not adding the differentiation here because differentiation we have some sort of already discussed in the form of operators. If you remember, you have to compute dt over small t or dx over dt from a data set. So this is basically covered in that aspect. Okay, so this topic in the course content will be having heading as numerical integration and differentiation, but I am calling it as a numerical integration because the only topic that we have is related to the numerical integration. We have to perform integration. So we have two branches. I will start from this side to integrate a normal function based on certain methods. Technically, we have to discuss only three methods here in this heading, and roughly three methods there. So total six methods we have to discuss under this topic to cover this topic completely. Okay, so three methods for integration only and three methods for solving first order differential equation. It is not difference equation anymore, it is differential equation. Okay, continuous variable or discrete. I hope you know the difference between these two. Approximate answers. Okay, and the strategy is based on numerical methods or numerical solutions. Okay, so let's move then. As I told you, I will start from this part. So let's discuss that concepts on numerical integration and what was the reason behind it, that to discuss this topic, and how do we do that? What's the theme of this? Because you will notice that if you understand the theme correctly, rest is just a repetition based on the accuracy of a same thing. What does this mean? You will understand now today. Okay, so let's move towards that application, towards this topic. Okay, so here from numerical integration, I am discussing basically the numerical integration of a function part. Okay, numerical integration. I know that maybe students of some of them are confusing, sir. If this is numerical integration mentioned there, why you put this numerical integration up of it? Student, numerical integration is a general technique, which is this part only. But this technique of integration would be applied on the differential equation solution as well. If you remember, if I ask you to solve a differential equation, so you need to do one thing. You have to integrate it. Okay, so when you have to integrate means you are solving analytically by integration. However, we do not want to do the exact integration here, so we have to do something called numerically. So this means that we are using a concept of numerical integration that we learned in this course and applying it to certain extent on the solution of the differential equations as well. So that's why I divided into two branches. Okay, although in a course content you will find that they are just written together. So mainly that's a big difference between these two. Okay, so there are few methods that we have to learn and then we have to apply to solve it on a differential equation, because to solve differential equation means that we have to integrate it. That's why numerical. So I'm just calling it again numerical integration, which means that I want to discuss numerical integration of a function f of x. कोई भी there is a function. What does this means that? This means that I want to discuss a numerical solution of a single variable function. I mean to say, for example, if I ask you to compute this integral, this is the integral symbol, a to b f of x dx. This symbolization I will use many times in this working. So f of x equal to this one. So you all know this is called definite integral. Definite integral, as it has the limits. Okay, definite integral a to b, and whatever be the answer is basically, you all know that from your preliminary analysis, that whatever be the answer I will get, we will get it by, let's say if I integrate this function, there is an integral of this function uh, is f of x. So I can say f of b minus f of a would be this, where capital F of a is the integral of this function. We are not solving it, so we are not interested, but let's say whenever we get the integral, we have to minus upper limit minus lower limit, if you remember that part. So whenever you solve it, you get some number, some answer. Okay, so there is no constant of integration because this is a definite integral, which means that you will get a finite answer. Okay, there is no ambiguity in your answer. So geometrically, what does this mean? If I plot this f of x, this is usually called integrand, if you remember. So I will use to call it integrand a lot. So integrand means the function that you want to integrate, and this a and b are used to call, if you remember, they are called limits. Upper limit is b, and lower limit is a. Upper limit and lower limit. We used to call it. We want to integrate it from a to b, which is lower limit to upper limit. So if I integrate, I will get some integrand, which is not a part of this code because we are not going to do anything analytically. But let's say if we integrate, then we will have to subtract upper limit and minus lower limit, so we will get some numerical answer. For example, 4, 2.9 or something. What that number represents, that's the point. So in graphically, geometrically, we all know that if I plot a to b, okay, a to b, then the graph of that function is represented. For example, the graph of this integrand will be represented like this one. Just a rough example. So y equal to f of x is there. So this part is here and this part is here. Okay. So I know that this is the lower limit and this is the upper limit, as this is x, this is y, and this is the graph of. So whatever be the answer I got by subtracting upper and lower limit correctly means that that number represents something. And we know from the our preliminary knowledge of the calculus at undergrad level is that this represents the area under this curve. For example, let me write down if the answer is capital C here, for example. This C has nothing to do with the constant of integration. Okay, do not mix it. I have used AB there, so I'm calling it C. If whatever the answer you get is C, so that C, in fact, rather than using a C, use it like that. Whatever the answer is capital A, this is area. So whatever the numerical value we have A by integrating exactly is basically represent this area. Area means the area under this curve and above the x-axis. So this is represented analytically if you solve it. Okay, we all know that one. Okay, so I just give you a brief recap. We are not going to use partial fraction, we are not going to use by parts, or we are not doing substitution. We do not have to do all these things because these all things are designed for analytical purpose when you can solve the integral exactly. What we want to develop a knowledge is that there are many integrals that we cannot solve analytically, or we can solve it but they are very time consuming. For example, just for recall, it is still a background. I have not started those methods that we have to discuss under this heading. Because student, if you don't know the background of the study, it is useless then. You just know that just you do the practice. So first you have to understand why we are doing this. Like what's the reason behind it? If our calculator can give the answer or we can solve it or we have learned it, this is again repeating in front of us. Okay. So for example, if I ask you to solve a simple integral, square e raised to the power x and integrate it to certain point. Okay, let's say we do not want to solve exactly, but let's say there is some point a to b and dx with respect to dx. If you want to integrate, you all know, sir, we have to apply by parts. And according to the by part, we have to suppose this as a function equal to some variable whose derivative needs to be computed, and this needs to be integrate, and then we have to do it something. If you remember, if you remember that if you solve this part, so you will have some situation. Maybe I'm writing something like that. Ex minus integral again of ex, if you remember. Okay, or something like this. You can verify it. For example, this is the answer. The point that I want to establish here is that it has a degree 2, so you need to integrate it 2 times. First time you integrate, by applying a by part, you will get this formulation, and now you have to integrate it again. So imagine that, for example, there is no power 2. In fact, the power is 100, for example. And I ask you to solve it. So if you want to solve it, you are 110% sure that, sir, we have to apply a by part there. So once you apply a by part first time, so you will get something like that. X 100, x 100, or x 99. You can see the main point is that minus integral x 99 e raised to the power x dx. Then to solve it again, you have to apply by part again in this region. When you apply by part again here, when you apply a by part again here, so as soon as you apply the by part again here, then you will get then you will get another relation which is something like that. X 99 ex minus integral x 98 ex and so on. This will continue. So you and then you have to apply by part again. So you know the method, but the integral is very lengthy in this case. So solving it analytically will take time. So is there any way that we can solve it? Obviously, you can solve it using calculator. But question is that if it is taking so much long time, then how the calculator can solve it in just a minute? It is not just because of the efficiency. Process is same. And the reason is calculator does not work on these analytical techniques that you have learned. They work on the numerical techniques. Numerical techniques that we are going to learn in this topic. Similarly, there are many other integrals which are very difficult to solve as well. For example, e raised to the power tangent something of tangent inverse of something or sine. So they are very complicated to solve it. So when they are so much complicated that you have to integrate, rather than using an analytical technique, we try to apply a numerical technique, because numerical technique does not follow the conventional way of handling the numerical integration. Okay, so I hope that the background is enough for this part, that there are two reasons to discuss numerical integration. One, sometimes we know the method that how to solve it. For example, here we know that this could be solved by using by parts, yes, that is two functions are multiplying, but the length of the question is too long. Sometimes the integrand, that is the function that you want to integrate, for example here, is so complicated I don't know how to find the integral of that. So we will try to switch to a method that can gives us answer, because this is definite answer, definite integral. We will get a some number at the end like this one for sure. But if we cannot find the exact answer a, so can we do something to get a approximate of a, like close to a? So this is the main theme of this topic. Like, okay, if you cannot solve any integrand or integral problem directly or analytically with exact answer, is there any way that we can solve it to get a some numerically approximate answer, like close to that answer? For example, close to, what does close to means here? That's I am repeating it many times. For example, the exact answer is 2. Exact answer is 2. So it does not means that approximate answer means 2000 or minus 200. No, approximate means it has to be very close to 2 as well. Like for example, it may be a 2.0001 or something, or 1.999 something. So it is not 2. So this is not exact, but they are very close to this answer. So we will try to figure out some other alternate method that can give something like this answer. If the exact answer is 2, can we generate something close to that? Then it is fair enough. As far as engineering application are concerned, we are not dealing with the exact uh, method like mathematicians do, but for engineering application problems, and if you have to solve some integral and which is very difficult to solve, or we can do it using calculator. But whatever the calculator is telling us, it's based on some numerical strategy. So in this course, you will learn as well what are those methods that can solve this part, and what is the strategy that can generate a solution numerically. So student, this is just a rough slide which I made it for you to, for a brainstorming or just to understand the topic that we are discussing today. Okay.